So what we're going to do today, sorry, I've just done this bit, so this is for the benefit of those at home. What we're going to do today is we're going to use logs to work out, if you've got a graph but no rule of a relationship that's curvy, whether it's an exponential relationship, whether there is a constant multiplier in the way whatever this is growing, or if it's something like this which starts from the origin, which might be x squared or x cubed, or it might be 2x squared or 3x squared, investigate whether or not there is a power relationship there. And we're going to do it by using logs to turn these graphs into straight line graphs, because straight line graphs, I can instantly describe those with a rule, and I can instantly tell you if something is a straight line. So I know that that line, if it starts with C and it's got a gradient at the end, that's the rule. Okay, so we're going to meet two sorts of curvy relationships. First is exponential relationships, and the other is ones where you've got x squared or x cubed or x to the power of 4, which I'm going to call power relationships. I mean, in general, I can spot the difference because power relationships start from the origin, whereas exponential relationships start from some initial value. But of course, it might be that this is 2x squared plus 3, in which case it would be up the graph. So it is complicated. So exponential relationships are of the form y is equal to some multiplier, y is equal to some initial value times a multiplier to the power of x. And I realised the other day we used k, and we may not have used the same letters. I'm only using the same letters that they use in the book for this particular part of the chapter. But we know, so we can straight away work out what a is. A is the initial value, we know that. But what we can't tell easily from the graph is a is this exponential, and if it is, what is the value of b? What's the multiplier? And then the power relationships, we've got some multiplier times x to the power of n. So we don't know if it's x squared or x cubed or x, and we don't know if it's 1x squared, 2x squared, 3x squared. The graphs all look very similar. And the way we're going to do it is by making them into straight line graphs. Carefully for this, because this is my least favourite thing in the first year. Okay, I'm going to start with exponential relationships. So let's say I've collected some data, I've plotted a graph, and I've got a graph that looks a little bit like that top curvy one. So my question is this something which is growing exponentially? Or is it just something that's going to maybe carry on going in a straight line? Or is it something that's maybe sort of sinusoidal? Well, here's what we do. We assume it's exponential. So I'm going to assume that it is exponential. All right? And that exponential equation has a power that's a missing value. So like we often do, I'm going to log both sides of this equation. And I can use whatever value I want. Because there are no e's in this, I'm not going to use ln. I'm just going to use standard vanilla log logs, log to the base 10. And then I'm going to use the log rules to split up that right-hand side, because the log of one thing times another is the same as the log of the first added to the log of the second. And then I'm going to use the third log rule Now remember, A and B are constants. X and Y are the variables. A and B are constants. So this is a constant value, and this is a constant value. So we've got the log of y is equal to some x's plus some constant. Now that rings a bell. Because that's what we've got here, isn't it? Except it's the log of y and not y, but a straight line graph has the equation y equals some x's, where that's a constant, plus some number. And that's effectively what we've got here. We've got the log of y, not y, but the log of y is equal to some x's plus some constant. So what this means is, and this might be a bit of a jump, but you just have to take my word for it. If we take this set of data, we've already plotted it once and realised it looks curvy, so we're thinking it's exponential. If we plot it, but instead of plotting y, we plot the log of y against the log of x. And if it is exponential, if our assumption is correct, this will give us a straight line graph. Because the equation is in this form here, some x's plus something. Where does that graph intercept the y-axis? At the log of a. What is the gradient of that graph, that straight line? How many x's are there in the rule? Log b. And so what we find is if we take our thing that we think is exponential and we plot it log y against x, not y against x, and you get a straight line, that indicates that you've got an exponential relationship. So a straight line confirms an exponential relationship. Now I have to tell you that this falls very squarely in the category of things that I don't remember, or things that I am unable to remember. So what I have to do every time I face a question like this is start here and go through that process, and that reminds me when I get to here that A, to test for exponential growth, you log the y-axis, and this intersection point is the log of A. Remember, A is the initial value. And the gradient is the log of B. And remember, B is the multiplier. A is the initial value of this exponential. B is the multiplier. So, let's have a look at an example question. What is that? Question 3. So this is on page 331. So we've got some data that we think is exponential. Yes, Sean?
What would happen if there was some constant on the end?
Some constant on
like
the
a, b, power x plus c?
We would get a... yeah, it wouldn't work, would it? No, so you can only do it where you think it's a straight exponential relationship. So we think we've got an exponential relationship, all right? It says it follows the trend. Let's say we want to work it out. So what we are going to do is we're not going to plot all of this data. what I'd like you to do is they've already taken the first pair of values, x and y, and they've logged the y value using log log. Can I get you to do the same for the last pair of values? And then can I just get you to sketch the line? Sketch the line, all right? So we're not gonna do an accurate graph here. That's pointless. I'd just like you to do what they've done to the 2x value, to the 9x value, and then do a bit of a sketch of the graph that you get. So you're going to have 1 point when x is 2 and 1 point when x is 9. And can I get you, when you've done that, to work out the gradient of the line joining those 2 points? And then can you also work out where it would cross the y-axis? So what you get here. So once you've logged your 9 value and got that, can you work out the gradient? So I'm assuming that we do get a straight line. So I'm assuming it is exponential. I'm just being lazy by only plotting the 2 points. So work out the gradient and then see if you can work backwards to work out where it would cross the y-axis. I know it's very bad, but we'll use rounded values. But I'm going to store the gradient, so I'm going to use rounded values here. Yeah.
Can I ask a question?
Yes.
How do you get the value of 8.2 from that? Oh, sorry, 5.2?
I did the log of that number.
Oh.
So they've taken the xy values and turned it into x and log y just by doing log log on the calculator of that.
Thank you.
And log log of that.
Right, cheers. Thank you.
So I get gradient of 0.531 blah 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 blah, which I've stored, and that's how far it goes up for every 1 unit along, so I just took away 2 lots of that to work out what this value was going to be. I get 1.037, so I'll store that in C, that would make sense, wouldn't it? So if we remember what we've done, we've said, right, if it's exponential, it can be described like that, but we've turned it by logging both sides and plotting it where the y-axis is the log of y. The number of x's tells us our gradient. Well, we can see the gradient from the straight line. I've worked it out. It's that. So I know that the log of b will equal that value there. How do you undo log to the base 10? We did that the other day. You do 10 to the power of both sides. Just like yesterday, we were undoing eing by lning. To undo log, you do 10 to the power of. And so what that does is tells me my multiplier. The gradient tells me the log of b, so unlogging that, doing 10 to the power of that, gives me my multiplier. Are we given a context? No, no context.
One decimal place.
Oh, does it say one? There we go. B is the multiplier. So whatever the context of this is, it is for every one unit you move along, it's what you're multiplying by. Okay? Straight line graph, the thing that you add tells you where you cross the y-axis. So I also know that the log of A is equal to 1.037. So I undo that by doing 10 to the power of both sides. Yeah, if it was only one decimal place, I was a bit silly to worry about storing it. So whatever this is, from that set of data, and we skipped the bit where we proved it was a straight line, but if we had worked out all of the points and plotted them, believe me, it would have been a straight line. From that, we worked backwards to work out what the initial value of this, whatever this was, is, and what the multiplier is. We did that by turning it into a straight line graph with clever use of logs. So it's looks now 332 question 7, 333 question 8. These are both exponential questions. The exercise is a mixture of the two, exponential and power relationships, but we're just doing exponential to start. It's enough to get your head around one. So let's now talk about power relationships. Might be referred to as polynomial, ones where you think it's squared or cubed. And so in this case, A isn't the initial value. A is the multiplication for the curve. With power relationships, they start at 0, 0. So my example of scale factor and area, if you multiply a shape by a scale factor of 0, its area will be 0. That's, so let's say we've got a relationship, it's curvy, starting from 0, 0, and we want to check to see what sort of power relationship it is. Notice this time, this is a constant. My variable is no longer in the power. This is a constant. So we're going to do what we did before. We're going to assume it's a power relationship, but we don't know whether there's a multiplier in front, and we don't know what the power is. Is it squared, cubed, whatever? We log both sides. Can I get you to do the splitting up bit on the right-hand side that we did previously? So the left-hand side can stay as it is, but the right-hand side, do that splitting up thing where we use the first log rule and then the third log rule, just like we did with exponential relationships. So I've got the log of y is equal to some constant, sounding a bit like it was before, plus some constant times the log of x. That's different. Before it was x times some constant. But it still looks a little bit like y equals mx plus c. It's just this time we haven't got y, we've got log y, but we've also got log x. So to test for a power relationship, you plot the log of x against the log of y. And if it is a power relationship, you will get a straight line. The y-intercept for that straight line will be log of a. Remember, log a is just what this relationship is being multiplied by. And the gradient, well, that's nice and easy. It will just be the power. So if it's a squared relationship, the gradient will be 2. If it's a cubed relationship, the gradient will be 3. And of course we can have powers between those two. You know, it might be x to the power of 2.5 or 2.1. How do I remember that to test for an exponential relationship you only log the y-axis? And to test for a power relationship, you have to log both axes. I don't. But as I go through this process, when I get a power relationship, I've got log and log, whereas with an exponential relationship, it was log and x. So I don't remember it, I just start from scratch each time. Although, of course, the questions often help you out. So here, they told us that it was an exponential relationship, and they sketched the graph where y was logged and x wasn't. So, you know, that is often helped as well. So what we'll start with on Monday is we'll do 3 examples of testing to see if we have power relationships and working out what the power and the multiplier are. So the story so far, which for those watching the video will seem a bit odd because I'm going to put Friday's lesson and this lesson together, so you will have just seen this, but we were talking about exponential relationships, and in fact we did plenty of practice of that last lesson, and power relationships. And both of these are curvy. Exponential relationships look like this with some starting initial value, and then power relationships look like that, starting from 0, 0. And you know, in that quadrant, it's not clear if it's squared or cubed or whatever. And so what we found was that with a little bit of log action, we could test if something is an exponential relationship by plotting log of the y values against the x values. And if you get a straight line, that means it's an exponential relationship. And the intercept and the gradient of that straight line tell us the things we want to know about that exponential relationship. So what we got to right at the end of the lesson, we said if we do the same thing to this expression, so we log both sides, and we could use any base, including ln. I'm choosing to use log log. And then use the log rules on the right-hand side. So you've all got this written in your books. And then third log rule there. We get a similar situation, a similar line that looks a little bit like y equals mx plus c, written the other way round. Log a is our value of c. Well, that's very similar to, I say very similar, it's the same as over here. But this time, the variable is logged, log x, and n is the same as the gradient. So what that means is, to test if something is a power relationship, we don't plot it like that, we plot it like this. Log of y and log of x. And if it is a power relationship, you will get a straight line. The intercept here will tell you the log of a, and we know how to undo logging. We do 10 to the power of, so we can work out if there's a multiplier involved. And the gradient of the line is the power. So the gradient gives us the power that we're after. So it equals n in that expression there. So we're going to do two examples, both from the textbook, page 331, question 3 and question 5. Page 331, question 3 and question 5. We're going to do the cheat that we did before. So we're only going to sketch the graph using the first and the last point. And in question 3, they've already calculated those for us. So we're not going to do what they say, plot all the points, do a line of best fit. We're just going to use the first and last point. We will be able to work out the y-intercept. That's what you get when the log x-axis is at 0. And you should be able to work out the gradient just using the normal bishop. So have a go at question 3. Again, not plotting the points, just sketching the graph using the first and the last points. And then similarly, question 5, just using the first point that you're given and the second point, the last point, which is the cow, go figure. You've got to do the logging for that one yourself, okay? So for 3 and 5, just first and last points. That means we don't have to plot any accurate graphs. We're just going to, no, we don't, because we can use the gradient to work out what the zero value would be. Have a go anyway, have a go. Page 331, have we all got a view of the book? Page 331, question 3 and question 5. So for question 3, I plotted the 2 points that we were given, first and last, didn't bother with any of us. Worked out the gradient, came out at 1.4. So the gradient tells me n, so I knew it was x to the power of 1.4. Now the definition of the gradient is how far the line goes up for every 1 unit you move along. I want to know the y-intercept, so I need to go backwards 0.48. So I know the line's going to go down 0.48, lots of 1.4. It started at 1.21, so it's going to go to 1.21, take away that, which comes out at 0.538. The y-intercept is log a. So I undo log a, that's log to the base 10, so I do 10 to the power of both sides, giving me 3.45 or 3.5, which is my multiplier. So I've worked out the power relationship by just plotting 2 points. We're assuming it's a straight line. If we plotted all the points, we would have confirmed that it was. We're assuming it is. Question 5, very similar. So we've talked about, so we're moving on now, sorry for those on the video, to talk about differentiating expressions involving e to the x. And we said that the reason that we want to describe exponential change in terms of e is that it's the only function which when you differentiate it, it doesn't change. So it's the only function that when you differentiate it, it doesn't change. And if it has a multiplier, which we know is our initial value, then good old peanuts and sweet corn, those pass through unchanged. Coefficients, as always with differentiation, that's not particular to e, that's just always the case, they just pass through completely unchanged. But we know that when we take a normal exponential expression and change it into an e expression, we don't just get e to the x. So we often get something a little bit more complicated. Maybe e to the power of 4x. And it's a very, very simple rule. To differentiate e to the 4x, the power stays the same, and then we just multiply by what you get when you differentiate the power. When I differentiate 4x in a normal expression, it becomes 4. So that's my answer. And if I combine those two things there, so y equals 7e to the 3x, then I know that dy by dx, well, I know the power will stay the same. It will always stay the same. It will be unchanged. The 7 is going to pass through unchanged, but I also need to multiply by what you get when you differentiate the power, which is 3. So that just becomes 21. And you know, I know we've done differentiation, we've done integration. It's easy to get the two mixed up and confused. We're not plus c'ing here, we are just differentiating. So can I get you to turn to page 326? Well, I say 326, it's always a bit of a magical mystery tour, isn't it? But 326-ish. And that question there, where you're asked to differentiate, when it says respect to x, it just means x is the variable, ignore that. Have a go at that. With the last one, as always, when you differentiate with brackets, multiply out the brackets first. Okay. What is it?
316.
316. Thank you, sorry. That's not the textbook, that's just my dodgy eyesight. 316. Thank you. So there are your answers. I said with E, just do the two terms separately. And then for F, multiply out the brackets, and it's a neat trick to remember that e to the x times e to the x, you just add the powers, so that's e to the 2x. So when you differentiate, you get 2e to the 2x plus e to the x.